Hello learners, welcome to Education Online program. I'm teacher Willa Lucia. So in our previous lesson we were talking about why we do not consider the vertical motion and the horizontal motion in projectile together. So we tried proving using the equations of motion. We had the first equation of motion, we had the second, so we're left with the third equation of motion. So what we are going to do first is we are going to draw our we are going to have our journey represented on the graph so that we can continue with the third equation. So we're going to have the vertical motion on this axis, the horizontal on this. Then we said our body was kicked from here and it moved in a curved way up to this point where it lands. So we say that this horizontal distance here, we shall call this horizontal distance Sx, and then we have our vertical distance right here. So we are calling the vertical distance Sy. We have the maximum height that the body reached before coming back to the earth. So we have it here, which takes us from the horizontal distance up to this point. There is our maximum height. So, and we have the velocity with which the body was moving. So we're going to indicate it right here to show us that there was velocity involved, because every time there is increase in distance, that means there is change in the velocity of the body. So we have it as u in meters per second. So that is what we had, and with the first equation of motion we came up with something like this, because we had our v is equals to ux. This was for the first motion, because we say that when it is horizontal, the motion in here is horizontal. That means that the body is moving with a uniform velocity. You see that your final velocity is equal to the initial velocity. And we say that for the vertical, we had something like vy is equals to, we shall have our initial velocity, which is uy, plus the g and then the t. Because this one is because the velocity of body moving vertically keeps on changing. There is variation in the velocity. So we had also the second equation of motion, where we say that the distance covered by this body when it is moving in the horizontal direction is equals to the distance, which is the Sx, will give us, because here we are saying that the acceleration is actually 0, so it is going to give us ux t, because you say that it is s is equals to ut plus a half gt squared. And then if your acceleration is 0, that means the whole of this cancels out. You'll be left with s is equals to ux t, which is what we have here. But then the second one, for the body when it's moving in the vertical direction, you find out that the distance covered will be equals to uyt plus a half gt squared. There is no change, because we say that in the vertical motion there is acceleration. For the acceleration due to gravity acts on that body. That's why you're seeing that it's there and it's not cancelling out. It is not 0. So now we are going to look at the third equation of motion. So with the third equation, what happens? We know that the third equation of motion for a linear body is V squared is equals to U squared plus 2G plus 2AS, but this time it is projectile. It is moving under the action of gravity, so the A changes to G. What if it is now a vertical, the vertical motion? What happens? You'll see that if we change it, having it in the matrix form, we shall have our V squared Y, and then our V squared X. The V squared X means that the velocity of the body when it's moving in the horizontal direction, and the Vy is giving us the velocity of this body when it's taking the vertical direction. So we shall have it is equals to the U squared Y, and then we have U squared X. So we have then plus our 2. What happens to the acceleration due to gravity when the body is in the vertical? That means that there is action of gravitational pull. The gravitational force there is not 0. We are going to leave the value of the gravitational pull as G. So what of the S? The S is the distance covered when this body is moving in the vertical direction. We are having it as our S, Y. So let's take a look at when the body is now in the horizontal, taking the horizontal motion. You see that in the horizontal motion still, there is no acceleration acting on it. So acceleration there is 0, meaning here we shall have our 0, but then we still have this distance here, which is the Sx. So now we are going to multiply our 2 inside the bracket. We shall have now a V y squared and Vx squared is equals to U squared Y and Ux squared. This is plus, taking your 2 inside the bracket will give you 2G Sy, and then 2 times 0, because if you multiply 0 times S, you're going to get that. Let me put this one times here so that it does not confuse. Now let's do the math, which will give us Y squared there, and then Vx squared is equals to, we are leaving this the same because there is nothing affecting this. Still, our initial velocity of the horizontal motion, we have it is equals to the final velocity. So that means that this one is also not a 0. So we have is equals to, this is going to cancel out. We shall be left with 2Gsy and then 0. You see that in your vertical motion, the velocity there squared will be equals to U, the initial velocity squared, plus 2 acceleration due to gravity and the distance covered when it is moving in the vertical direction. But then in the horizontal, what happens is that the acceleration cancels out. So that means we do not have the distance here. We shall have it as our Vx squared is equals to our Ux squared there. Now you see that these are the reasons as to why the vertical motion is considered separately from the horizontal, because you see that they do not have common factor of this acceleration of pull. So the acceleration of force here, it will always act on this object when it is coming downwards or going up, but then when it's just moving direct on horizontal surface like this, that it does not act on that body. So this is why we are having the difference. So let's take a look at some other things in the acceleration, in the gravitational motion. So in the gravitational motion, you'll find out that at maximum height, we always consider our velocity v to be equals to 0. So it can either be the final velocity if it is the stage 1 of the motion. But then if it turns to the second stage of the motion, it becomes the initial velocity of that body. That means that there our u is equals to 0, because if you look at this, assuming this is how our body is moving, so this was the initial velocity the body was given to move up to that point, and then up here, up to down, is our at the maximum height. So this stage here, this first one, for it to go from here to reach up to the maximum height, is the stage 1 we are considering. So we can take it as A. So from this maximum height coming back to hit the ground is now our B, another stage. So what I'm saying is that when this body reaches this point here, it is the final velocity for the first stage, because here we had given it already initial velocity from the point it was kicked. So when it reaches there, it gives it its final velocity, which is equals to 0. That is for A. But then when it comes to B, this point here becomes its initial velocity. That means at this point here, for this section, our u will be equals to 0. Then you see that our final velocity will be at this point here. So this one becomes also different. That's why I'm saying that one stage, the final velocity of one stage becomes the initial velocity of the second stage. So you'll see that when it is dropped from a height, that means that if you're getting the distance here, since we are having our u is now 0, how would you get the distance here? Our distance is equals to, we are saying that it is u ut plus a half is equals to ut plus a half gt squared. But then we are saying that this one is equals to 0. So it's going to give us s is equals to a half gt squared. So what of the velocity? If your initial velocity is 0, what will happen to the final velocity there? You will find out that the final velocity here will be is equals to, because it is v is equals to what? U plus gt. But in this case, our u is equals to 0. What happens is that when you substitute 0 here, our v will be equals to only the acceleration due to gravity acting on the body and the time taken for the body to move. So this is how the motion keeps on changing when it reaches the maximum height there. So you'll see that if you want to get the velocity squared, which is equals to u squared plus 2as, at this point, if you reach the maximum height and the initial velocity there is 0, that means we shall have our v squared giving us 2as. So those are some of the important things we should be noting with when you're dealing with the projectiles. And there is also something very important, that if you do not want to use this, and they were telling you to find the height covered by this, moved by the object, how would you do that? You can use conservation of energy, the principle of conservation of energy, to do that. Because if you look at conservation of energy, what happens is that energy is neither wasted or it is created. It will just change its form from one to another. So you see that from heat it can change to sound, from sound it can change to something else, but it is not wasted or it cannot be created. At this point here with projectile, you'll find out that the body can either change from kinetic energy and to potential energy, or it can change from kinetic energy until the point it will attain both kinetic and potential energy, and then it will come back to the potential energy. It depends on where you're starting the body from. So you'll see that So we shall see that, because here, if they want you to find the height, you see that our S is representing the height. But then if you don't want to use the height, that's why I'm saying you can use the principle, using principle of conservation. Of energy we can say to calculate the maximum height. So we see that when you started the body from rest, if that this is the ground, and then you kicked it from this point here, it reaches this maximum, what happens is that it is changing its energy from potential here, then to kinetic energy. Because we are saying that potential energy is the energy this body possesses due to its rest, when it is at rest. But with kinetic energy, it is the energy the body possesses when it is in motion. So you'll see that when it was first here on the ground, when you give it an initial velocity, it is now moving from changing its energy from this potential. Since it is moving, it will attain kinetic energy and then comes back to potential again when it is at rest. And then we shall have it as our potential energy. Shall have it as our potential energy is equals to kinetic energy. So what's the formula for finding potential energy? We see that to get potential energy, you need to know the mass of the body, the acceleration due to gravity acting on the body, and then the height with which the body has moved. If you come to kinetic energy, we are going to get half, then we have our mass, and then the velocity with which the body is moving, but then it is squared. So this is the formula for getting potential energy, and that is for kinetic energy. So how do you use this to get the maximum height? To get the maximum height, we know that when the body is moving under the action of gravity, the mass of the body does not affect the motion. Even the shape of the body does not affect the motion. So that means that, you see, that is our mass here is going to cancel with the mass when it is attaining the kinetic energy, because the mass is the same. We are still dealing with the same object. So we shall have here our GH to give us a half V squared, because we have eliminated the mass. We divided through by the mass to cancel it out. So if we have like that, we still have our H there. We want to make H the subject. How can we make the H the subject? We can make it by dividing through by the coefficient of H, which is G. You can also make the V the subject to also know the velocity with which the body is moving. So we can either have it as our G. Our GH is equals to G, which is equals to a half V squared. So different, you also divide it by G. So we shall have our GH. Okay, this G here, let's just eliminate it direct from there to be left with H is equals to instead of a half, we are now having 1 over 2G, because we are multiplying our G with that. It does not cancel out, but it multiplies. So we shall have it as our V squared. So we shall get this as our H is equals to V squared over 2G. This is in case you know the velocity with which the body is moving. If you do not know the velocity, how would you find the velocity from the same formula? To get the velocity there, now to get the velocity there, since you have your potential energy is equals to kinetic energy, we shall have it as our GH equaling to a half mv squared. So if we have that, what happens is we can multiply our 2 on both sides to remove it from here. So we shall have our 2 times mgh is equals to 1 over 2 mv squared times 2. So we are multiplying 2 on both sides to eliminate it from this side and take it to the other side of the equal sign. So we shall eliminate this 2. Here we shall be left with 2 mgh, which is equals to the v squared. Now we are going to divide by the coefficient of the velocity, which here is the mass of the body, which we shall have it as is equals to m, and then here equals to m. We shall cancel that, and then this m will cancel that mass. We shall have our 2gh is equals to v squared. So if it is like that, remember you cannot find it when it is just square. You have to introduce the square root sign so that we can take the root to this side. We only want the v to be the only subject there without anything squaring it. So we shall introduce a square root sign on both sides to give us 2gh is equals to v squared. So we introduce here over the square root sign. We shall have our 2gh is equals to v squared. We introduce the square root sign on both sides. So this 2 here will cancel with the root to give us 2gh is equals to v. That means that the velocity we shall be finding here at maximum will give us root of 2gh. So this one is applicable if you also know that the height with which the body has moved. So if you know this and that, then it becomes easy. That is if you want to use the principle of conservation of energy. So there is also another thing we need to know is the time of flight. How do you calculate the time of flight? Since we say that time of flight is the total energy, total time taken for the body to move from the point of rest until where it hits the ground. And we are saying that for it to move from ground up to the maximum height, that time taken there is equivalent to the time it will take from the maximum height until it reaches the ground. Meaning that if you're going to get the time t, which is the time of flight, capital T, is equals to the t, okay, because if this is our journey, assuming this is the journey, the time from here up to here, the maximum height here, is equals to the time taken from this time up to here. If this one is t, then this one is time t seconds. So we shall get our t plus t to give us the time of flight. If you have it like that, meaning that we can add our t, then plus another t. So our time of flight, which is the capital T, our time of flight capital T will give us 2t. So this is the formula you will use when they want you to find when they want you to find the time of flight. So for today, I think we've seen so many things about the calculations. We've seen why we consider the motions separately. I mean the vertical and the horizontal. So this is because of the difference in the acceleration due to gravity. You find out that in the vertical there is action of acceleration due to gravity, but in the horizontal it is not there. And then we see that at maximum height, what happens is that our velocity at maximum height is also is also 0. So if you look at the horizontal motion also, what happens is that in the horizontal motion, we mean that the velocity is uniform. When the body is moving with the uniform velocity, you find out that the initial velocity that you start the body with is equals to the final velocity. That the velocity the body comes to rest with is the final velocity. So the two velocities are equal when you're considering the horizontal motion. So with this, we come to the end of our lesson for today. We shall learn more about this, our projectiles, in our next lesson.